Great, thank you so much. Thank you for the introduction and the invitation. So welcome everyone. So today I'll be talking about this topic of continual visual learning. And before I go through this topic in detail, I just wanted to give a brief introduction to the institute that I come from. So INRIA is a French National Computer Science and Applied Math Institute. And for those of you who don't know, these are research centers all across France that you can see here, pretty much everywhere on the boundaries of the country and not so much in the middle of the country. So there are 9 centers at the moment, and I come from the one that is here in the southwest of France, southeast of France, Grenoble, which is a research center, the third oldest, I think, research center of INRIA in France. So we are based in this building, and this is where I am at currently. And it is in a city which is sort of the heart of the French Alps, Grenoble. So there's a couple of rivers, and there is mountains all around the French Alps. And just another view of the city from the top of a hill that is called Bastille. And that's about it for the quick introduction about where I come from. And today I'll be looking at this topic of continual learning. And this topic has been given sort of different names over the past, 20 or 30 years or so of research in this domain. And it is known with other phrases such as incremental learning or lifelong learning, sequential learning, or never-ending learning. So there are maybe very, very subtle differences amongst all of these, but they all together kind of roughly represent continual learning, which is the idea of being able to learn continuously. So let's take an example of this in real life, right? So I have origins in India, and growing up there, I was taught to learn what is bread, and this is what I was used to growing up. So roughly, a form of bread that you find in the Indian subcontinent in several countries. But as I grew older, I started to travel and then go to other countries and live in different places, and then I learned other forms of bread, which looks nothing like what I grew up with, but I still know that it is roughly representing the same thing, and it is something that you eat together with your meals, and so on. But despite having learned this sort of new concept of bread, so to speak, I still haven't forgotten these rotis or chapatis, the Indian form of bread that I grew up with. So roughly this is the idea that we are trying to target. Can we have a similar sort of learning framework for machines, wherein you start with sort of learning a particular task, for example, learning the task of recognizing or being used to the type of bread that I showed from the Indian subcontinent, and then I can confidently say, okay, I can now solve this task of recognizing this form of bread. And then I move on to a different task, which is very related to my first task, but of recognizing still bread, but of a different type. Okay, so then I move on to baguette, and then I can confidently say, okay, now I can solve this task to this new task, but I can also still continue to solve my initial task of 1, okay, of recognizing the bread from Indian subcontinent. And eventually, I can move on to other tasks, which may be completely different, of recognizing, let's say, other forms of food, and then become a powerful machine. Here is a slide I kindly borrowed from, I was allowed to kindly borrow from Professor Hyung-Hee Lee from Taiwan. The hope is not to create machines that scare us, but are hopefully helpful. So let's take one step back to see what is happening in what we can call as standard machine learning, right? So typically what we have is a data set of different sizes, either a really large one such as ImageNet, or maybe a smaller one such as Pascal VOC, which predated ImageNet on the same type of tasks in computer vision of recognizing images. So typically most of these data sets, what we have is a decomposition of this data set into 3 distinct sets: the train set, a validation set, and a test set, right? So we train our models on the training set, then we learn the parameters or the hyperparameters of the model on the validation set, and then eventually we test this model that we have learned on a new set of data that we haven't seen, which we call as the test set. Okay.
I'm so sorry, but your slides doesn't move.
The slides don't move. Sorry about that. You're not able to see any of them?
We just see the first one.
Oh, that is strange. So you haven't been able to see any of my slides so far then?
We have been looking the first one. I can see that there is a bottom slide show, maybe and play. Maybe it can help.
That's what I did, right? So how about this? Do you
The
see
same.
still the first slide?
Yeah.
Okay, so let me do this. Let me unshare my screen and then share again. Let's see. Okay, let's see now. I think it got paused. Now, how does it look?
Yeah, it works. Thank you.
Yeah. Okay, I see the problem. Okay, sorry about that. So I'll quickly go back to this example that I used earlier on and go through it very, very quickly, right? So here is the example that I took earlier on, where I said, growing up in India, there were certain forms of bread that I grew up with, this rotis or chapatis, and then having traveled to different countries, I learned different forms of bread, and eventually, I learned these new forms of bread, but I still remembered, what I grew up with. So the bread from, the Indian subcontinent. So this is the idea that we want to take and build onto into a machine learning framework for computer vision, where you start with solving an initial task, task one, and then you move on to learning a new task, task two, for example, could be the two types of bread in task one and then in task two. And then now after having solved task two, we can confidently say that, okay, I can solve both tasks of recognizing the two types of breads, and then move on to other, other tasks. Okay, so let's then see, I was talking about the standard machine learning framework where you have a training set, a validation set, and a test set, right? So this is the standard setup that, we've all been using for the past several years. And the main sort of underlying core assumption of this framework is that, all of these data sets, the training, validation, and test sets, all come from, are sampled from the same distribution, which is an important assumption that we make, in that what a model has been trained on initially is the same distribution of data that we are going to see in the future, and we are able to test and then recognize the different elements that, are shown in these samples. Okay, so this is a great, setting for benchmarks and what I, call as academic data sets. But then, in this type of framework, we are able to solve many of these benchmarks and academic data sets, starting from small data sets for image classification, such as Pascal VOC, to moving on to larger data sets, such as ImageNet. Okay. Whereas this standard machine learning framework is sort of reasonably okay for real world systems. So you're seeing many of these machine learning models being applied and deployed in the real world to a large extent, but we're still limited in solving a much more challenging problem of what people have been calling as embodied learning, where, let's say, you take a robot which has been learned to do certain tasks in one environment, and now you want to take this robot and put it in a completely new environment which the robot has never seen. For example, it could be taking, let's say, an autonomous driving system that learned to drive in the Western world, and now you want this to put it in a different setup, such as the Indian subcontinent, like in India, where you expect the system now to be able to automatically transfer from what it has been trained to learn in the West to a completely different setup in the East. So clearly there is a huge challenge that now this autonomous driving system has to adapt to. So here we are clearly severely lacking in today's state of the art. Okay, so with that in mind, I wanted to talk about sort of the spectrum of supervised learning frameworks that we have today, and then kind of put continual learning in this particular context. Okay, so here is the standard, the supervised training setup that we have. So we have a training data set, right, that we use to learn a model, which I call here as the learner. So now this training data set is for one particular task T1, and all the data samples X and their corresponding labels come from a data distribution D1. Okay, and now in the case of the test scenario, what we have is another set of samples that are again sampled from the same data distribution D1, but now we don't have the labels here. Why? We want to estimate these labels and see how well we do. So we don't have these labels during the training phase. Okay, so that is the standard kind of supervised learning setup. And here, we have a spectrum of different learning frameworks that we see, starting from multitask learning to transfer learning to various other things, including continual learning. So I'll briefly talk about these frameworks to see, how they're related to each other. So the first one is on multitask learning. So clearly, as as the name says, what we are interested in doing is to learn a model that can handle different tasks, starting from task T1, T2, etc., to task Tk, right? So each of these tasks has its corresponding data distribution Di, right? Now we have all of these data from which we sample the data samples X, and we also have their corresponding labels Y, right? Because it is a supervised learning framework. Now, given all this data, we then learn our model, okay? And in the case of test, what we have is potentially samples coming from any of these data distributions, right? For any of these tasks. So to give an example in the context of computer vision, what this could be is, let's say, the task T1 represents image classification, right? To give a label to each image. Task T2 could represent, the task of detecting the different objects that you see in the scene. So essentially, draw a box around the different objects that you see. And task TK could be, for example, image segmentation, where you want to label each and every pixel. Okay, so all these are different tasks, and we want to be able to learn a model that solves all of these tasks. Okay, so then we move on to transfer learning, where what we have is two tasks, a task which is a source task TS, and then we have a task which is a target task TT. Okay, so we have data from both of these distributions, DS and DT, respectively. And first, initially, we learn a model on the source set. Okay, and then we use this model that has been learned on the source set and then transfer, let's say, the parameters of this model to learn a new model, or to update the new model with data from a transfer task or target task, okay, TT. So this, for example, could be cases where, let's say, you have a lot of data that is available in your source domain, DS, and very few samples, let's say, in your target domain. So it could be, for example, transferring between domains such as standard natural images that you see, DS such as ImageNet, which has a lot of samples, to maybe a completely different domain of, let's say, images from the medical domain. But still, there are some characteristics that could be useful for us to transfer, in terms of knowledge. Now, what happens here is that in the end, we are only interested in the target domain, right? So that's our target, and that's what we would like to evaluate and predict in the test scenario. Okay. Okay. So then is another related task of domain adaptation, where you have data again from two different distributions. You have a source domain DS, and then you have a target domain DT. But in this case, the task is the same. So this could be, for example, let's say you want to classify images of the real world, such as images that you take with your smartphone. That could be our domain DS, right? And you want to classify what each of these images represents. And then our target domain could be images or pictures of paintings, right? And you want to, let's say, now classify these paintings into what they represent. So, right, the task is still the same. You want to classify a given image, but the domains are very different. So you have a source domain of, let's say, real images versus a target domain of paintings. Okay. So then we have other frameworks such as meta learning, which I'm not going to go about because it's a little bit more involved and we will not have time to cover it, but cover all the details. But here is another popular framework. Then we have what is called as sort of online learning. So this is kind of getting closer to the continual learning setup, where you have a task T1 during the training phase, and you get samples in a sequential manner, right? You get the first sample X1, with its corresponding label y1, and then you get the next sample x2 with its label y2. Again, both of them from obviously the same data distribution d1, and so on, right? So now you get these samples sequentially, right? And then essentially your model has to kind of learn in an online fashion. So you don't have all of the data in one single time instance, right? Like you have in the previous cases of transfer learning, domain adaptation, etc. You get samples one after the other. Okay, so this is the online learning setup, and then the prediction is the same. So you still, at any point in time, you're given a sample or a set of samples from the test set, and you want to be able to predict what labels are represented by these samples, right? Image classification, you want to label, what class each of these images represents. Okay, and the final thing that is the topic of our tutorial today is that of continual learning. So it is related to online learning in several ways. In that you again see a sequential arrival of data, but now in the most generic case, you have different tasks coming in at different time instances. So in the beginning, you get, let's say, task 1 with its corresponding data distribution D1, and then you have data samples X, which are sampled from this, and then you want to learn and to be able to solve this task properly. Okay, and then at another time instant, you get another task and its corresponding data distribution and all the samples, and now you want to be able to learn or update the current learner model with this data. Okay, so when we look at the test scenario, what happens is initially when the model has been trained only on task 1 data, so you can get test samples only from this data distribution, right? But whereas now, once you have seen both task 1 and then at a future time instant task T2, you get data samples in the test case from both of these tasks and the data distributions D1 and D2. So you essentially want to be able to say solve all the tasks that you have seen so far. Okay, and so on. So in the generic case, you have k tasks, and when you're trying to evaluate the learner model at time instant, let's say k, you can get data corresponding to any of the previous tasks, right? 1 through k, and you want to be able to accurately recognize all these models. Right, so let me just very quickly check to see if there are any questions. Okay, I don't see any. All right. Okay, so that's the sort of, let's say, a short overview of the landscape of some of the supervised learning frameworks. Okay, so there are other learning frameworks such as unsupervised or self-supervised, if you like it, and semi-supervised. But for the moment, fully supervised case, these are some of the learning frameworks that we've been seeing, the past, few decades. Okay, and there are others, but we're not going to talk about those in the context of this tutorial. So we will be focusing today on this continual learning setup. Okay. Okay, so what is this incremental learning or continual learning setup, right? Again, we can interchange these different terminologies. So what we have, like I said, is a sequence, the arrival of data as in the form of a sequence. So you have different tasks arriving at different points in time, and then you want to be able to learn a model that can handle all of these tasks. So for example, in the case of visual data, so task T1 could represent, let's say, recognizing different types of animals. Task T2 could be recognizing, let's say, different flora, different types of flowers. T3 could be different vehicles or forms of transportation. T4 could be different sports, and so on. Okay, so here there are different types of incremental or continual learning cases that we can see. One of them is that of task incremental. So we move on from one task to another, like the example shown here. Another one could be that of class incremental, where let's say you want to how do I say, the example I gave earlier of, let's say you want to recognize different forms of bread, right? So you're just moving on from, let's say, bread from the Indian subcontinent to bread from, let's say, France to bread from other countries, and so on. Okay. Another one could be that of domain incremental, where you have, let's say, the task of classifying images. Excuse me. And these could be images, let's say that were taken for example, during the day, images that were taken during a particular season, spring, let's say. Now you want to move on to images taken in the winter, but still recognize, what is depicted or shown in the image, right? So that could be sort of a domain incremental or a domain continual learning setup. So there are many forms of these incremental learning frameworks that exist, and we'll be looking at sort of at a higher level picture, but then I'll give you a few examples of a couple of these learning setups. By the way, I should have mentioned at the beginning, so please, if you have any questions, don't hesitate to send them across in the chat, and I'll be breaking the presentation up into 3 parts, and then at the end of each part, I'm going to take the questions that have shown up. Okay, so this topic of incremental or continual learning is a classical problem actually in machine learning, as some of you may be already aware. And this has existed for several decades, right? Going all the way back to the mid-80s and even slightly before in certain cases. So it's not something that we've just come up with now. And there have been, people have been looking at it in different ways, and there are some methods that have been proposed, and there are different kind of variants of these methods. So one of them is what is commonly called as zero-shot learning in the machine learning world, where it is kind of the extreme case where you do want to be able to recognize, let's say, new classes, but unlike the setup that we talked about so far, there is no training data at all for these classes. So essentially, there are 0 training samples for these new or unseen classes during the training framework. And now you want to be able to kind of generalize your model to this zero-shot learning setup. Another group of works is one which uses, the simple kind of idea of where you want to continuously update the model with updating the training set. Okay, so what we want to do here is we want to keep the data. So essentially you saw data for the first task, and then now you want to keep this data, and then whenever you get data from the task 2, you now train the model jointly on both of these tasks, and then you continuously do that. So this is another way of dealing with this problem. A third alternative solution here is for us to kind of use a fixed representation, right? Fixed data representation. In that, so you have a model, right? So I didn't really go into the basics of learning 101, but I assume many of you are already aware, is basically when you want to train a model, you first need to be able to represent your data in the form of some representation that you've chosen. Could be, let's say, a deep learning framework, which kind of gives you a feature representation, or let's say a vector that transforms your data into this form. Okay, so now typically, what has been happening in the last, let's say, 20 years or so in machine learning and computer vision is that we don't want to have a representation that is manually computed. We want to be able to learn this representation, right? So what we could potentially do is, okay, learn this model for representation, and then have a second part to the model which does the classification. And what we can think of doing is fixing this representation, right, with the initial training data that you had for the task 1, and then you simplify the learning problem and only learn the classifier as and when you get new data. So I know I'm skipping a few details here, but we'll go through this in a bit more detail in a few slides. Okay, so this is another way of kind of tackling this issue of incremental learning, is by kind of simplifying the learning problem and decomposing it into learning the representation and learning a classifier, okay, to recognize, let's say, what is in your images. So by fixing the first part of learning the representation, you kind of simplify the problem, and it makes it easier to address this kind of continually learning setup. So that is one way of dealing with it. And now we'll see sort of the pros and cons of this, especially these last 2 frameworks that I talked about, of continuously updating the training set versus using a fixed data representation, right? So here is, let's say, the original model that you have. So here I'm using a deep learning framework as an example, where you have the test image that goes in as input in the first layer of your deep learning network, let's say a CNN, for example. And then the last layer of the network essentially does your classification into these tasks, right? So you have these tasks that your model already knows to solve. So let's call them as old tasks 1 through M, okay? So now we have been given a new task, right? Shown here in orange. And now our goal is to be able to extend this initial model, excuse me, to this new task, as well as handle the previous set of tasks that we had, right? Okay, so here is the kind of the first brute force kind of solution, which is not incremental in that you kind of keep all your data, okay, and then you train the entire network. Okay, so here you see all the blocks here, which are kind of shaded, which means that all the parameters of all these layers are also going to change. And now we have the task of learning this new, we have the problem of learning this new task, which given the data and the corresponding labels in this supervised learning case for all of these tasks, we can clearly solve this problem, right? So this kind of typically is referred to as sort of a, I call it the golden baseline, because this is the best thing that we can do, right? Have all the data, keep all the data, and then you keep training. So clearly it is a brute force solution because you're not really exploiting what all has been done, and you're not kind of learning it in a continual or an incremental fashion, okay? So we should be able to do better than this, but this is the best thing that we can do, but it comes with certain drawbacks, as we'll see. So here, just to go through it in a little bit more detail. So what is happening here is we are kind of retraining the, let's move this away. Okay, so we are retraining the full model with both the new and the old data, right? So you have, like I said, a part of the network that corresponds to your feature extraction, and then you have a part that corresponds to your classification. So M task, you'll have M different outputs here, and now what we are doing is adding a new bunch of nodes that correspond to the new classes that we have added. Okay, you can have one or multiple classes. So here is an example of 2 classes that have been added, and you'd get the corresponding nodes that have been added also to the last layer of the network, right? So clearly, one of the big drawbacks of this is the computational expense, right? So clearly doing this and learning the entire network all over again by reusing the existing and the new data is expensive, okay? But other than that, it brings other interesting challenges or issues, is the fact that we need access to this old data, right? So this can lead to issues such as there can be storage capacity limitations, right? We may not be able to store all the data. Fine, data stockage is not that expensive now, but at certain point we do have to draw a line and say, okay, I cannot really store any more than this. But more serious than that are issues of privacy, right? We may not be able to, for example, store all the data because maybe the data that we have access to comes with a certain license that we can only use it once and we cannot reuse it several times. And clearly, like I said, there are scalability issues as well, right? At certain point, this way of kind of retraining the model on the entire data set kind of breaks, okay? In terms of scalability. Okay, so we want to be able to do better than that, right? So these are cases where you have no access to all the data, right? It can be, that can be one reason. Another reason can be that, okay, maybe you have limited resources and you cannot store all of the data, right? And another interesting issue that comes here is actually, it is very popular for us for people to use an existing model that was pre-trained on some other data set. So we don't have access to the data set directly, but we have access to the pre-trained model. Now, what we have is, this pre-trained model, which was trained, let's say, on a large quantity of data. So it is very useful, but it has been trained by others and they are unable to share the data, but we only have the model. So here in this case, so we really have to look at alternative ways of extending these previously learned models, because there is no way for us to access all the data. Okay, so those are our let's say the requirements, because of which we want to do it in a learn in an incremental fashion. So there are a few simple solutions that are possible in the beginning. So first one is that of where we keep pretty much the entire network as frozen. That is, we don't change any of the previous layers of the network. Okay, and all we have is just data for the new task and the labels or the ground truth for the new task, which means that we will only be updating the new layers or the nodes in the neural network that you've added. So this corresponds to the third example I was talking about, where you kind of freeze or use a fixed feature extraction or a feature representation. So all of this network was trained on previous set of classes or tasks, and we're not going to update them, but we're only going to learn the new part that we have added to the network. So this is a reasonable thing to do. It's not so bad. And this is typically called as fine-tuning. So here is one extreme case of fine-tuning where I said where you don't train any of the previous layers, you only train the last layer and the part that you have added to the network. So this is admittedly one extreme way of doing fine-tuning. But here we're only using the new data. So we're not storing any of the old data. But clearly the issue here is that it leads to suboptimal results, as we will see in a couple of slides. Because this is not completely unexpected, because the features that you've extracted were tuned or learned on the old set of data or tasks, which means that they are not very appropriate for the new data that you're seeing. Okay, so we need to do solve this problem. Okay, so another solution is that of, okay, so we'll say, okay, I'll do my fine tuning, but I will do, let's say, not just my last layer that I've added to my model shown here in orange, but I will also fine tune, let's say, some, or in this example here, all of the previous layers that you have seen. But critically, the important difference between the brute force solution is that here you're using only the new data. Okay, you're not using any of the old data that you have had access to when you trained the initial set of tasks, but you will only do it for the new data that is given. So clearly what is happening is the model is now kind of drifting towards the new tasks that you have that you're going to see. Okay, so what happens with this is a phenomenon that is known as catastrophic forgetting. So this was a phenomenon that was identified a few years ago already, a few decades ago, I should say, but it is kind of extreme, as we will see now in the case of modern deep learning architectures. Okay, so for that, I'm going to take an example here of object detection. So here is an image, right? And let's say the model has been learned to detect 3 types of objects, including the class person, right, shown here in the green bounding box. And it takes the image as input, and then it predicts, okay, where are all the different people in this image and 2 other classes. Okay. Now what I'm interested in is to extend this model to the class of horses. Okay, so I had 3 classes initially, but now I want to move on to a 4th class, horse, and now I would like a model that detects not just the class of person, 2 other classes, and as well as the new class horse. Okay, so essentially the goal is now to be able to detect this horse shown here in the green box. Okay, so these are now my 2 models. So A being my old model, right, shown here at the top, which can detect 3 types of objects, including person, and B at the bottom is the new updated model, which can detect not only person and the 2 old classes, but also the new class horse. So essentially all the 4 classes that I'm interested in. Okay, let's see what happens in this case. So here is an example I'm showing of a model that was trained on 20 classes, right? So the model A, let's say, is the initial one, which let's say is now trained on all of my classes, okay? Which is essentially serving as a baseline for us to compare how well we are doing. And I'll call my first 10 classes as the initial set of classes, okay? So which is my old set of classes, and then I'm showing the accuracy of detecting these classes in this particular table. So you get, let's say, 68.4 is the accuracy of detecting the first 10 classes, and 71.3 is the accuracy for detecting the new classes, which are classes 11 through 20, right? And the accuracy, just as a reference, of detecting all the classes is just under 70. Okay, so now what I do is look at this setup of A and B, where now I train my A model, the initial model, only on the first 10 classes, right? So clearly I can only recognize my first 10 classes, which I called as my old set of classes, and the accuracy here is just under 66. Okay, so yes, it is not significantly lower than the inaccuracy of baseline when you have all of these 20 classes. So this is expected because clearly you're seeing only roughly half of the data, right? So the model is less robust to all your classes. Okay, but it is a reasonable accuracy, right? Between 68 and 66, there is a drop, but not a dramatic drop. So now let's see what happens when I take this model A and I add the new set of classes 11 through 20, right? And now end up with this model B. Okay, so essentially what we are doing is we are training this model A with a new set of classes, right? So this is the fine-tuning model that I talked about, where you use only the new data and its corresponding ground truth to retrain the entire or fine-tune the entire model. Okay, so with this, what happens is pretty dramatic, right? So first, we see that this new retrained model performs very, very poorly on the old set of classes, right? Because the model has sort of drifted away from the where it was initially to where it is now with the new set of classes 11 through 20. So in a sense, it has kind of forgotten what it was able to detect pretty well previously. Okay, but on the other hand, the kind of model is doing reasonably okay, right, on the new set of classes. So it is roughly, let's say, 65 compared to 71, what it was in the baseline. So baseline will always be higher in this case because it's the best that we can do, learning on all of the classes jointly. But as an illustrative example, you see here, when you don't have access to all of them and you only have access to the new set of classes, this is what happens to this kind of naive solution that we referred to. Okay, so overall, clearly the average is it's pretty disappointing. Okay, so this is the phenomenon of catastrophic forgetting. So clearly, this number of just under 13 varies depending on how many of the layers you have fine-tuned. So if you keep some of the layers as frozen, that is, you don't change those layers, the drop in performance may be less, but still it is tens of percentage points no matter what you do. Okay, so so it is a serious issue that we need to address. Okay, so essentially why this is happening is because there is now no guidance for us to kind of retain the information that we have from the old classes, right? So that is the issue that that we need to handle. Okay, so let's see, kind of now establish some set of rules or desired items that we want in our incremental learning setup. Okay, so what we want in our incremental learning setup is to learn from one task after another. So you have a sequential learning of tasks. So I said, it can be one task or multiple tasks at different points in time. Okay, ideally we also want to be able to do it by not storing data from the previous tasks, right? So this would avoid issues such as privacy and issues with being able to store all of the previous data samples, etc., etc. Okay, in addition to this, we also want to have a reasonable memory footprint for our model, right? Clearly, as the model is learning newer and newer tasks, you expect the model to grow, but we don't want to grow it exponentially. We want to keep it reasonable in terms of the increase in size of the model over time. Okay, and finally, what we also would like to do is we would not want to maybe forget the old tasks that you have already learned. Okay, so these are our ideal requirements, right? So we don't live in an ideal world, so we do make certain assumptions or certain simplifications, let's say, of these rules that we have. So instead of not storing any of the data samples, what we maybe relax this constraint is, okay, we don't want to store many data samples from the previous tasks. Okay, we want to store only a limited number, if at all. Okay, in terms of the growing of the memory footprint, we don't want it to significantly grow over time. We clearly allow it to grow, but perhaps let's say linearly compared to exponentially. Okay, the last requirement that we had of not forgetting any of the old tasks, perhaps we could relax that by saying, okay, we don't want to completely forget the old tasks, so a little bit of forgetting is okay, because there is, let's say, a limited capacity for my model, and I would like to maybe forget some of the concepts, or allow a little bit of forgetting, because I can't remember everything that has happened. So just like us, we sometimes do forget things, so we should allow a model to be able to also have this luxury of forgetting. Okay, so what we're going to see further is kind of a flavor of different approaches. So the field is fairly vast in terms of the different approaches that people have been proposing, including some of our collaborators and several others in the research community. So we clearly don't have time to go through all of them, but I picked a couple of examples from each of the different types of approaches that we are encountering these days. So we can categorize them as into three broad categories of methods that are based on regularization, methods that are based on the idea of rehearsal or replay, and then there are another class of methods that are based on kind of making changes to the architecture of the model. So I should again add that we are looking at it from the perspective of, of deep learning, and we want to be able to adapt existing modern deep learning frameworks for continual learning. So there are three broad ways of being able to do this. Okay, and then depending on the time, we will look at other learning frameworks. So continual learning, for example, in the context of self-supervised learning. So this is some of our recent work that we're going to present actually next week at the CVPR conference. And finally, I'll end with some takeaways. Okay, so let's see. So this is a good time for me to quickly check if there are any questions. Let's see. I go on the chat. Okay. Right. Okay, I think. Okay, so I only see questions about the issue with the slides that was talked about earlier, but yeah, sorry about that. That's fixed now, but I don't see any questions at the moment. Let me also check in this platform. I don't think. Okay, good. Okay, so we can then move on. So yeah, please don't hesitate to ask questions at any point in time. Okay, so let me just go back. All right. So we'll continue with going through the methods of different continual learning approaches. So the first one is what I categorize as regularization based approaches. Okay. Up. So let's see here. Okay. Up. Okay. So what this does is going or exploiting a standard but very powerful idea in machine learning and optimization is to kind of, okay, you have a loss function that you're optimizing when you're training your a deep learning framework, and what we do is we kind of adapt this loss function, especially when you're training the new task. Okay, so what we do for that is we add a regularization term to this loss function. Okay, and this the idea of adding this loss is to penalize the catastrophic rating that we encounter. Okay, so we'll see this in a little bit more detail. So even within this category of regularization based models, we have, I'm just checking again if my slides are visible. Okay, good. Yes. Right. So there are two subcategories, let's say, in the context of regularization-based models. The first one is one that is focused on the data, and there is a second class which is focused on the model or the prior that you have in the learning framework. Okay. So right. So let's see what is this data-focused regularization. So what this does is exploit an idea known as knowledge distillation. Okay, so simply put, the idea is here for us to actually preserve the responses that we have of the previous model. So basically, when we have a new task, right, we will still be kind of fine-tuning the entire network. We will be learning the new layer that you have for the new tasks. But what we're also going to do is we are going to learn the last layer corresponding to my old tasks. But in this case, we're not going to use the standard loss, because we don't have any samples that correspond to my old classes. I only have samples that correspond to my new tasks. Okay, so what we're going to do is we are going to store a copy of my model, okay, the existing model. And what this does is you can send your samples, the new data samples, through this existing model, and then get the responses of your current model, okay, which corresponds to only your old classes. So here clearly, this old model has never seen this new data, so the responses that it gives will not be very appropriate for these particular tasks, but it will still give us an idea of how this network was performing on all these new samples, right? So now, so you essentially have a before and after case where once you have the previous responses that you get from the model, okay, before it was updated, and then now you have new responses of the model when the model has been retrained or fine-tuned with the new data, okay. And essentially what we're looking at is a difference between how the model is changing with respect to its previous state, okay. So let's see what this means, okay. I'll come back to this in a different algorithm, okay. So essentially what we're trying to do is making sure that whenever a model is changing, we are kind of ensuring that it doesn't change completely. So we're kind of always, we have two copies of the model, right? We have an existing copy of the model which has seen all my old classes, okay. And then we have a new model that we are updating, okay, from this current model. And but once we have used the new data to update this new model, you essentially get the new responses for all of the the last layer nodes of your neural network, okay. And what we then do here is we impose a new loss which essentially compares the new outputs that you're getting versus the outputs that you get with the previous copy of the model, right, for all the initial layers. So essentially these are the nodes on which we impose this distillation loss. So essentially we're trying to distill the information that you had in our old model to the new model by making sure that the difference between these responses between the old versus new is not significant, okay. So clearly, we are adding a new loss term. There is another hyperparameter in terms of adding the importance that we want to give for this loss term, or versus learning the new task, right? So for the new task, we use the standard loss function, okay. At this point, I'm not showing the equations, but we'll come back to these in a little bit later on, right? And then for the new task, you have the standard loss, which is the cross entropy loss for learning these new classes, okay. So this is a standard framework. So one of the popular examples of this work is that of Lee and Hoem from about 6 years ago now, and this works reasonably well. And in fact, in some cases, despite the method being very simple, it has shown very good results, especially when the old and the new tasks are very related, okay. So on the contrary, this type of approaches has kind of shown poor results when the tasks are very, very different, right, when they're unrelated, so to speak. So, and then there is a question also in terms of, that you do need to store the old model. So essentially the size of the memory footprint is double, but it's only 2 times. So it is not extremely large, but it depends really on the type of architecture that you're using for your deep learning framework. So if it is a really large model, then maybe there is a significant cost in storing in storing this this old model as well. Okay, so that's that. So there is another sort of related idea here. So previously, I can just go back to a couple of slides. What we did was impose this loss function only on the last layer. Right now, a good extension to this could be actually, oh, let me not just measure the difference in responses in the last layer, but I'm going to do it at several intermediate layers, right? So this box here or block here represents several layers. Okay, so we could have this kind of cost that is computed at different points in the neural network. Okay, so that was this work done by Douillard and his colleagues a couple of years ago, where they introduced this idea of pod or podnet and distillation based on that. So basically, you can pod essentially is for pooling and then distilling. So basically here you can pool, let's say this is your intermediate representation, right, which is 3-dimensional in terms of C channels and the width and the height of the feature representation, and you can do different sorts of pooling in terms of just the width. So you end up with a representation that is in the number of channels and the height of the feature vector, or you can do a height pooling and end up with a C versus W sized feature vector. And you can introduce these poolings, the distillation losses at different with different types of pooling. So here is one with the width pooling, where you have pooled over the width the responses or the intermediate responses from the previous version of the model T-1, and you're measuring the difference between the current version of the model T, so the updated model versus the old model, right? And then you're looking at a difference. So this is a new term that you can also add in the loss function. Okay, so again, it is a related and a simple method, and it has shown very good results for related tasks. But with this particular podnet, the results for unrelated tasks is unclear. And also there is a question of, again, you need to store the old model, which can be a significant cost in terms of depending on the type of the network that you have. Okay, right. So that was the subcategory of the data focused regularization. So now we'll see a slight variant of this in terms of model focused. So previously we were using this or defining this loss function L on the responses, the edge or the last layer response, etc. But now we're going to directly impose these constraints on the parameters. Okay, so theta are the parameters of your network. So you have parameters that have been updated after you have seen n tasks. Okay, theta n, and then you have parameters that you have learned in the previous step, right? That is theta n-1. Okay, and now what we are doing is imposing a constraint on the difference between these weight vectors. Okay, difference between these weight values or the parameter values, because we don't want the parameter values to change completely, right? We do want to keep the network because you're only adding, let's say, one task compared to the 10 previous tasks that you have seen. Okay, so we expect the network to change a little bit, which means thetas will change, but we don't want all of the thetas to change, and we don't want all of them to change significantly. Okay. So again, so there are different kind of even subcategories of methods that we can come up under this by saying, okay, we can do this clearly in the extreme case for all the thetas in my framework, but as you know, there are millions and in some cases billions of parameters in my neural network. So having to do this over all of them is perhaps not necessary, especially given the computational costs that you will have to do by doing a linear pass on all of these, or maybe even more efficiently, but still it's fairly expensive. And more importantly, all of the parameters are not critical for measuring this importance. So right, so people have also come up with excuse me, using weights for weighting, saying, okay, some of the parameters theta are more important than the others. Okay, so we have different variants that are possible for this importance of parameters, and that kind of changes the regularization that you're doing in this model focused approach. Okay, so one example here is that of elastic weight consolidation from a good number of years ago now already, from about 5 years ago or so, where you kind of give an individual penalty for each of the of the parameters, and the way you compute this lambda is from the Fisher information matrix. Again, it's not important in the context of today's tutorial what and how this is, but just to say that there is some ways of calculating this these weights from the statistical information that you can gather and compute from this data. Okay, so the idea here is kind of roughly this. So let's say this is the in a simple case of a model which only has two parameters. Okay, so I'm showing the parameter space when you learn let's say the parameters for the task, the first task 1. So here everything that is shown here in white or light color has a low loss, has a high loss, and everything that is in blue has a low loss. So clearly, when we want to do optimization in the space, we want to end up kind of somewhere here, where it is kind of the lowest possible loss value that we're going to make for a choice of theta 1 and theta 2, right? So you start with some initialization randomly, and then you do your stochastic gradient descent or your favorite gradient descent approach, and you end up with the best possible solution in this theta 1, theta 2 space. Okay, so now let's say we have moved on from task 1 to now learning on task 2, where clearly the how do you say, the space of the optimal values of theta 1, theta 2 has completely changed, right? Because it's a completely different task. And now you start with this initialization from your previous task, right? Which is this yellow dot shown here. And you then perform again the stochastic gradient descent with your fine tuning operation, and you end up with optimal solution in this space, because here there has been no regularization, right? This is when no distillation has been, or regularization has been applied. So this is locally good for task 2, but if you look at where this point is in the case of task 1, so clearly it is not ideal, right? We wanted to be more like in this space for task 1, but we ended up here, right? Because of task 2 completely changing it. So now what we want to do is kind of use the information from task 1, either like the other regularization approach we saw, data focused, or we now want to see a model focused approach where we want to introduce a regularization on the thetas, right? So we want to rather move in this horizontal direction and end up in this space, which is ideal for both task 1 here and also for task 2. Okay. Right. So that's essentially what this this approach of elastic weight consolidation is trying to do by measuring this. So this is another visualization of that, which I'm going to skip now. So right. So the good thing or the great thing about this approach is actually that it is agnostic completely to the architecture, right? So we only interested in the thetas and the lambdas, which is like Fisher information matrix that we can compute from all the parameter values that we have, right? So we don't really pretty much care about the architecture. So, and it also, on the other hand, has shown good empirical results, right? But the slight drawback of this approach is that it's kind of very locally valid moves that we are kind of making, going from one to another, and especially when we take this high dimensional space or super high dimensional space with millions and billions of parameters, it is not great, right? And the issue that can be serious in certain cases is that of storing. But here we don't store the entire model, but we are storing the importance weights. So we do store weights for all of the millions of parameters, but we can then use some ideas like sparsity, because most of them are pretty much, let's say, 0, because we don't want to impose this regularization on maybe all of them. We want to do only a small how do you say, weight on some of them. So you can use ideas from sparsity and sparse vector or matrix representations to kind of reduce the amount of storage, but still there is some cost involved in kind of storing these data. Okay, so I'm just checking the time. So we're just over an hour in. Okay, so maybe we'll quickly check if there are any. Right, so I'll take this question that came up a few minutes ago. So for the question is, for pod, you also need to use the training data from T1 to evaluate the performance of the old model, or is there some trick you can use if those data are unavailable? Right, so in this case, actually, we are not using data from the previous classes, right? So that comes to another type of approaches, which is the rehearsal-based approaches. So we only have a previous version of the model. So you have stored pretty much the entire model that that you have for the previous time instant, and what we are looking at is only kind of passing the new samples. So we don't use the old data, we pass new data through the old model and the new model, and then we look at the difference in the responses, the intermediate responses. So it is very much similar to the other case, okay, except now that instead of computing the differences at the last layer, we also compute at the intermediate layers, okay? So we don't use any of the old data. Right, so we will come to using the old data in the next type of class of approaches, let's say. But before we go there, so I just wanted to summarize that we saw one example briefly of what model-focused regularization is, and there are several alternatives, which some of them I've listed here, such as memory-aware synapses, moment matching, PathNet, etc., etc. So there is a broad range of methods that have been proposed in this subcategory of regularization methods. Okay, so with that, someone, okay. Right, so there's another question on, was it tested for how many additional tasks can these approaches be used for? So this is a very interesting question. So this depends on the methods. So the typical methods that have used, I think, is maybe to the order of tens or hundreds number of additional tasks that have been added. So I think that is roughly the the state of the art at the moment. So clearly there is a lot more work to be done in terms of going to much larger number of tasks. So it's at the moment tens or hundreds, I would say. Okay, so let's move on a little bit. Right, so then we have the next class of approaches, which is called as rehearsal or replay. Okay, so in this, the idea is that okay, instead of deciding that okay, we're not going to store any of the previous data samples, we're going to relax this assumption and then store, let's say, a couple of examples from the previous task. Well, I say a couple, maybe a few tens or few hundreds, for example. An alternative could be is instead of storing directly the samples, we could have a generative model that will generate these samples, right? But then there are important questions of how many of these samples you want to store, how do you select these samples, and then how do you use these samples, okay? So here is one approach called as ICAR from just over 5 years ago now, where what it does is it's sort of the first type of approach where it stores a couple of examples from the previous tasks, okay? And it produces ways or defines ways of selecting samples that are kind of closest to the feature mean of each class, right? So I'll explain this method in a little bit of detail. And then it uses the same idea of knowledge distillation that we had, okay? And it has an interesting use of the memory of how much and how many of these samples you're going to store, okay? So but before that, what this approach does is first actually split the problem into 2 stages, right? So there is the first stage that I talked about of learning the features, right? And there is the second stage of learning the classifier given the features, right? To be able to classify, let's say, your images, okay? So here is the kind of overview of our algorithm. So of the training phase of the algorithm, where you have, right, your training examples xs to xt, right? So these are our new training examples at any given state, and then there is a memory size, that is defined by k, and then your model has already been trained for s-1 tasks, right, previously, which means you have some set of current model parameters theta. Okay. In addition to that, unlike the previous setup, we are now storing a fixed number of samples per class or per task, which is denoted by the set calligraphic P, where P1 represents the set of samples from task 1 and PS-1 from task S-1, which are set of samples that are chosen. You can call it as exemplar sets. Now what we do is, in the training phase, we are going to update our parameters theta by essentially called as updating the representation using all of my new data, right, shown here by xs through xt here. Then we also have our exemplar set P, right, which are selected samples from my previous tasks, and then the previous set of parameters that you have. Okay, so that is done. Now, once the representation has been updated, we then have to kind of reduce the number of samples. So we have a fixed memory set of k samples. So until now, we were using, let's say, each task had k divided by s-1 samples in the memory, right? But now we need to reduce some of the samples for the previous s-1 tasks. So we do that operation of reducing this exemplar set, and then we construct a new exemplar set. We'll see how. And what this now gives us is a new exemplar set, now going from P1 through PT. Okay, previously it was still S-1, but now we have seen more tasks going from S to T. Okay, so now the exemplar set is from 1 through T. Okay, so that was the kind of learning the representation part, which is kind of the first step of this split of the problem. Okay. Then now you have the second step of classifying, right? So here they use this idea of nearest mean classifier. So it's a simple classifier where what we do is compute the mean of each of these classes or tasks, right? So you have T tasks in your exemplar set. Now you take all of the samples in P1 and then you compute their mean, which gives you a respective mean mu y for a task Ty. Okay, and then for a given sample that you're trying to classify, you just simply look at a new sample X, right? You compute its representation by using the updated representation that you have. Then you look at which is it closest to in terms of all the T means that you have for the T tasks, right? So this is very simple. I can skip this very quickly. Okay, so now we'll see what is happening in this update operation, right? So in the update operation, so you have right, the new data set of tasks S through T. You have your same, the exemplar set for all the S-1 previous tasks. So now we make up a combined training set of all my new data samples, right, XY, and all my exemplar training samples from my old data set, okay, of your previous tasks. So now after this, we train the model as it is with this new set of data, right? But now we have two types of loss functions. So previously you had the standard loss function, which is the cross entropy loss, which is applied on all the new data samples, right? That you see from S to T here for all the tasks from S through T. That's the standard cross entropy loss. And in addition to that, we have a distillation loss. So like previously I was saying, you look at the difference between the responses of the model, the new model versus the previous model, right? So we're going to do this, but we're going to compute this only on the exemplar samples, right? So here the summation only goes from 1 through S-1, which are the S-1 tasks, okay? And then you do a log loss here. We can use different forms, so which is looking at the responses that you get with your updated model versus the previous responses that you have from the old model. So you have stored again the responses of the previous model, and now you're getting the new responses of the old samples, right? So if we kind of forget these equations for just a second, so what we have is the same idea of regularization, okay, of the difference between how the new model behaves versus how the old model behaved on these samples, right? So previously we were doing it for all of the new training data, but now we are doing it only on the old samples which we have stored. Okay, so that's the minor difference. Because we have access to the old samples, the old network is meant for these old samples, right? So so we can then train this model on these old samples and the old responses. Okay, so that's the minor difference that we have. Okay, in addition to storing these samples. So clearly, this method is is making a clever use of the memory. So it is not exploding the storage issues or the storage problems of the model, but it's kind of limiting it, okay, to making a choice of, okay, I can store k samples and this is what I will do. So there is a potential issue, right, in this method, in that you do need to store examples. So if you have issues of privacy, then it's not the method that you should be applying. Okay, and it is also limited by the memory capacity of the model. So the more clearly samples that you're storing, the better is the performance of this method. Okay. Okay, so let's maybe quickly take another Q&A break to see if there are other questions. Okay, I think I answered these two. Right, so there isn't any other new questions. I'm going to carry on. So we have just under 20 minutes, if I see correctly. Okay, so we talked about one method for rehearsal, a rehearsal replay, which is that of iCal, where you're storing the samples. So now we'll see the alternative of generating these samples. So here is one example from a few years ago, which uses the idea of a scholar, which is essentially a composition of a generator and a solver. The solver is the classifier or the model that makes our predictions eventually, and the generator is the one that generates the samples corresponding to my previous tasks. Okay, and what is done in this replay methods is that you're learning this generator and the solver in every incremental or continual time step. Okay. Okay, so what let's see here. What we have here is a simple training procedure. At any given task, what we have is a new scholar that is learned. Okay, and for learning this new scholar, for example, let's say scholar 3, we use data from task 3. Okay, so I'm saying one task here, but it can be multiple tasks. We use the new data from there, and then in addition to that, we also use the data that is generated by the previously trained scholar, right, at task t-1. So for task learning scholar 3, we use data from task 3 as well as data that is generated by scholar 2. Now this scholar 2, the assumption is that is able to generate data corresponding to both my task 2 and also my task 1. Okay, so that's the idea here. So let's see what happens in the training procedure. So you now have to train both the generator, right, and the solver. So first we'll see what the generator training is like. So you have data from the new task, which is task T, okay, and then you use the data that is generated by the old scholar or the scholar for the task t-1, right, that generates your samples x prime. Now you use both of these data samples, x, the current task, x prime for all the previous tasks, and then update your generator model. Okay, so I'm not going to go through the details of this, but as a because you can have any type of generator and any type of solver, and this method is still equally applicable. Okay, but the overall idea is you treat it as a black box for the moment, these generators and solver blocks, and just given old data through this replay x prime and the new data from the current task x, you can generate a model. Now we go through the solver. where you have the current data and the current labels X and Y respectively. And then you have your replay, which is data generated by the previous caller, X prime, and then the samples, the labels that are generated by my previous solver from the previous caller, T minus 1, giving rise to labels Y prime. And now you have X, Y, and X prime, Y prime. And using these data samples, you can update your solver model. Okay. So here the big advantage of this kind of approaches is that it avoids memory issues because you're not storing all of the data samples or even a subset of the data samples, depending on how big your generator model is. You can have a much more compact way of storing the previous data. But one issue is you could potentially have accumulation of errors as you go from one scholar to another. You can kind of make errors and expand them, make them pretty serious, depending on the type of samples that you're generating. Another issue is on the control of the class of the generated samples. So a scholar T can generate samples from 1 through T tasks, and controlling it can be a little bit tricky, right? So you can have conditional generators which address this issue to a certain extent, but not always. Okay, so maybe in just a couple of minutes, I'll go through this third class of approaches, which is that of architecture-based methods. And here I'll take the example of PACnet, where the idea is, very intuitive in that you have, let's say, if here we're looking at one layer and one filter in a layer of a neural network. So each of these is a node in your neural network, and there is a corresponding weight or theta parameter associated with it. So what we do is we learn this filter for task 1, which means all the weights have been updated. And after that, we do a pruning step where we discard some of the weights, okay? And essentially what we're trying to do is make space for new tasks that we're going to see, okay? So here, let's say in the first step, you prune 60% of your filter weights, right? And then you retrain with data from new task 2, okay? But here we may give a constraint that you fix the parameters of the ones that have not been pruned, right? Shown here in this dark gray color, and then you only learn the weights that have been pruned after learning task 1. Okay, so that essentially makes some space for task 2, and now you repeat the process. You prune some of these orange nodes corresponding to task 2, and then you move on to another task. Okay, so this is one way of doing it for all the filters of all the layers of your neural network. So this is a work from a few years ago as well, which is still pretty actively used actually. So the big advantage of this class of approaches is that you have a fixed memory consumption, right? But the disadvantage or the drawback is that you do need to know the total number of tasks in your framework, right? And it has been shown to be pretty powerful and avoids this catastrophic forgetting issues. So that's the kind of the third class of methods called architecture based. Okay, so here I just wanted to show a very quick comparative analysis. We won't go through it in detail. I'll leave the slides for you to access them. And this is coming from actually a journal paper from a couple of years ago from several researchers in the community, where they've evaluated different types or different categories of approaches and compared to see which one works better than the other on 2 data sets called Tiny ImageNet and iNaturalist, which have kind of different statistics going from few tasks to a few tens of tasks tens of classes per task to a few hundreds of classes in the iNaturalist data set, and also very differently sized data sets, okay, with iNaturalist being significantly bigger. Okay, and here we see the performance of each of the tasks. So task 1 is the one that is learned first, and then you see the performance, how it evolves as you keep adding other tasks, right? So you'll have 10 tasks here, which means you'll have 10 points on this graph. So on some methods, you see a significant drop in performance as you're adding new tasks. So that is the fine-tuning approach that you see here in this dotted line at the bottom. in the first column on the left, whereas the approach on this a synapse-based approach shown here in red seems to work reasonably well. Okay, there is a baseline, or the golden baseline, of training all of the models jointly, which is still quite far away from these other approaches, incremental learning approaches, and then you see the behavior for all the other tasks, right? So in all the cases, you see that the performance goes down for fine tuning, whereas for some of the other methods, it remains more or less stable and being pretty flat. Okay, and task 10 is the task that you learn right at the end, so you don't expect a huge drop in performance for this task here, because you just have one single data point. Okay, so this was on the tiny image and the iNaturalist dataset. So I'll kind of summarize my my tutorial talk at the moment with the general trends that have been observed is that typically the rehearsal and replay based methods, they work pretty well, but they only pay off when you have stored a large amount of, or a sufficient number of samples. Okay, and this approach, which I briefly mentioned at the end, based on architecture based frameworks of PACnet, it works, I think, pretty much the best across the board. And then there is methods. I talked about the elastic weight consolidation, EWC, but there are other more recent approaches that are also more robust to this than the EWC. So maybe to answer a few questions of what is the kind of model that you should be using, is in general the larger models give more capacity, but they do come with a drawback of overfitting. In terms of the deep learning architecture, a wider network is better than a sort of a deeper network, so to speak. And another set of observations is that the regularization that you introduce, it can interfere with learning the new set of classes. Okay, so clearly there is a balance that needs to be maintained between learning new classes versus learning the old classes. And also that it is observed that dropout works usually better than sort of this weight decay that is typically used in training these deep neural networks. So these are some of the takeaways from this paper. Okay, so this other learning frameworks for self-supervised, unfortunately I will not have time to cover this, but I will leave these slides online, and this is a work actually for those of you attending CVPR next week. You will be seeing it there. So I will just end with a few takeaways of what should we be looking at into the future for this domain of continual learning. The first one is that the desiderata that we have is that we want to have a constant memory. We want to have models that are kind of task agnostic for the future. Like here I said, okay, there is first task, then there is a second task coming for training, then there is a third. So we do know when new tasks keep arriving, but we don't want to be aware of the tasks that are coming, but we do want to move to a setup which is more agnostic. There has been some work recently in this domain, but still a lot more needs to be done in terms of moving to a really continual learning setup where you just get data and you don't know whether it belongs to a new task or an existing task that you've already learned. And then ideas of forgetting gracefully, like clearly we cannot remember every single task that we have learned. Maybe there are certain aspects of the task that is okay to forget. And finally, data sets are still an issue in this particular domain. And as I heard at a recent conference that somebody quite famous said that they don't like data sets because it's more of a problem than a solution, because it creates biases, it creates issues, and we do clearly need to work on improving and creating better data sets which are more adapted for our problems. Okay, so with that, I'm going to end my tutorial. And then I have a few minutes left, so I'll be taking the few questions that are there. So Aikal, using feature mean could lead to misclassification because it discards class feature boundary data. So indeed, ICAL is limited to the, how do you say, the boundaries of classes. So there are alternatives or improvements that people have talked about, where you do like this Voronoi diagram of handling these boundary cases, where you just don't attribute it to one class, but you have kind of a weighted neighborhood, and you look at these boundary cases. So you just don't use a single feature mean of a particular task, but you can use multiple feature means for multiple tasks, and then look at a weighted combination of that. So there are improvements to this. So this kind of borrows ideas from many years ago of nearest class means. Right, so the next question is on PACnet. Sounds like training many separate smaller networks. Is this intuition wrong? I don't see what is the additional aspects, I guess, of PACnet. Wouldn't you achieve something similar, of you just train neural networks for separate tasks and use inferences from one that has the most reliable output for a specific? Okay, so yeah, this is a fair point, right? You can think of having different neural networks for different tasks, but then there are two things. So this is called as typically the multi-head learning framework, incremental learning framework, where you already know, let's say, which task your data corresponds to, and you go directly to that particular head and then you evaluate it. Or you can evaluate all of them and then try and find the most confident output. But clearly there are issues in doing this because they are all learned separately. You do need to do some sort of regularization or balancing of the outputs across all these networks, because they are completely trained independently. So you do need to kind of manage them. And also a big limitation of this would be the expansion of the memory footprint of the model. So every new task that you see, you would create a new model. So there are pros and cons. So I'm not saying it is not to be done, but on the contrary, the advantage of PACnet is that it fixes the memory footprint, and you know how much you're going to pay in terms of your memory, and you can continue with that. So there are kind of, I guess, hybrid approaches you can look at between the two. So yeah, so both of them are feasible indeed. Okay, so the next question, I guess, is more on the practical side. Where can I find the slides? So I'm going to share it through the conference organizers. I didn't share them before because it was being updated, but I will make sure that they reach all the participants, so they will be linked. Oh, I see the question was updated. No, okay, it's still the same question. Okay, so we still have 1 minute. If there are any more questions, I'll be happy to answer them. But if not, thanks to everyone for your participation. I can't seem to get this thing. Yeah, sorry. Okay, so we still have maybe 1 minute, and then okay, so I see the question was just updated with typos. Great, thank you very much. Okay, so I think we have officially come to the end of this session.